Okay, so take two on 20.3, number 23. We have a vector field E that's proportional to to r over the magnitude of r cubed. And I think this was the helpful bit, remembering that the book, when they write r, they mean x comma y comma z. Why do they mean x comma y comma z?
R? It's the radius.
It's just the point.
It's the radius given a
So what they're thinking, right, is like, here's a point, x comma y comma z, right? The radial vector that goes from the origin up to that point is this r vector.
Okay.
Good with
This
that?
is radial because it's basically a sphere.
It's the row, like, this would be where I would draw and label row, right, if I was doing spherical. Yeah, so this is just a radius vector, kind of. Okay, so the first thing I want to do is calculate the curl of E, or at least convince myself whether or not it's 0, right?
Mm-hmm.
Okay, maybe I should actually calculate. So what's the magnitude of r cubed?
Square root of 3.
The x squared plus y squared plus z squared to the 3 halves.
Oh.
So my vector field E, right, is kx over x squared plus y squared plus z squared cubed, comma, ky over x squared plus y squared plus z squared cubed. Oh,
They
well,
have a square root in it.
they better have a square root in it. So that's to the 3 halves power. Right, because I was getting norm to the 6th power, right? And then we got a kz over the same business. X squared plus y squared plus z squared to the 3 halves again.
Could you use parentheses in this case? Like
Could I use parentheses?
the quotation parentheses, like to show like it continues on.
Sure.
Okay.
Do you have all those on the bottom to the 3 halves power?
I do. Because the magnitude of a vector, right? So magnitude of this vector r, right, is the square root of x squared plus y squared plus z squared. Right? And then I need to take that and cube it to get the magnitude cube.
Oh, I see.
You guys all good with that?
Yep.
Okay, so now I need to calculate the curl of this thing. Yes?
Mm-hmm.
At the very least, I need to calculate one component, right? Because I suspect the components are all going to be pretty similar.
Mm-hmm.
Okay, so what's my first component of the curl?
The f of
Is it 0? Got it.
partial of f of x over partial of y.
Wait, hang on.
F of z over
Okay, so it goes z.
y.
You taught me this trick.
Yeah, I did. I'm sorry.
So it goes z, y, and then
X,
some other
y,
stuff.
X. Yep.
And this will be the partial
Y,
with respect to y, and the partial with respect to z,
Mhm.
right? Okay, so in my first component at least, I need the partial of the f component with respect to y. You guys all see that? So what's the partial of the z component with respect to y?
0 because there's a z at the top.
It's not 0.
It's not? Okay.
2y.
There's a y in the bottom, right?
Darn.
So I think I get a kz, right?
Okay.
And then I've got this stuff to the negative 3 halves power, right?
Okay.
So I'm going to get over that stuff to the 5 halves power. So I got x squared plus y squared plus z squared. And then I need what? Times the derivative of
Well,
the inside, right?
times 3 halves times 2y.
Oh, thank you. I need to take my power down.
Right.
Power down, stuff to the 1 lower power times the
Oh, that would be x squared. No,
derivative
that's
of
just
the
times 2y.
inside. So I need the y partial, right?
It's just 2y.
So I get a 2y here.
Okay.
All with me on that? Okay, and then we're going to subtract, and we're going to get a similar thing constructed for the z partial of the y component. Okay?
Mhm.
So power's the same, so I'm going to get a negative 3 halves. I'm going to have a ky still. I'm going to have all this junk, x squared plus y squared plus z squared, to the 5 halves on the bottom again.
Well,
Times
2z.
And then I'm going to have a times 2z.
Which is practically the same thing.
Correct.
So you will.
That one's 0. What's your next component going to be?
X minus
Z.
z, so
Okay, so we need the partial of fx, partial of fz, subtract. They need to be with respect to
z in respect to x.
z in respect to x. Are those going to be different? Do I expect
No.
anything to end up coming out different here?
No.
No.
Not really, right? I expect it to be a negative 3 halves k x times 2z, right, over the same stuff. And this other guy, my other thing, right, I expect to be the opposite of that. So I'm pretty sure I'm going to get 0 out of this, right? Okay, so part A, I calculated the curl of E, and I got 0, right, as a vector. What does that tell you? Like, what was the thing we learned that predicated this whole business?
It's now a gradient field.
It could possibly be a gradient.
It could be a gradient with.
Gradient. Okay.
I know. Curl finds gradient field where divergence finds curl field. Was it?
Yes.
Yeah. So what I found is that there's this thing that I kind of vaguely recall about the curl test, which is when you take a curl, if you get 0, then maybe that thing is the gradient of some function, right? In other words, I'm looking at this now and I'm speculating, maybe this is gradient of some function f, right?
I think that's the other one that tells us that. No.
No, it's curl.
Oh, okay. Okay.
Goes in that direction.
So, am I right in thinking that? What does the curl test actually say?
If curl
It
of
needs to be a
whatever
smooth
equals
vector
0
field.
vector,
Oh yeah, it needs to.
Has the property with the loop thing.
then you
Okay,
get
so the
gradient.
curl test needs
The curl has to be
Is-
smooth.
Yep.
3 things, right?
Mm-hmm.
Okay. Is E smooth?
Yeah.
Yes.
I think so. Right.
Yeah, except for maybe at the one problem at 0, right?
Oh right.
But on its domain, is it smooth?
Yeah.
Yes. You guys see that? The point of non-differentiability isn't even in the domain, right? So it doesn't make sense to call it a point of non-differentiability because it has to be in the domain to call it a point of non-differentiability. I got the curl of E is 0, and then what's the other thing in the curl test that
Oh,
you
it's
need?
the bubble
rubber
wrap
band.
test
No.
where you just wrap.
No, it's this. It's
Oh,
rubber.
it's the rubber band one. Okay.
Okay, the curl test, right, is because we're thinking which theorem has a curl in it? Which one of the big theorems has a curl in it? Stokes has a curl in it, right? So I'm thinking Stokes at this. So Stokes is a thing about surfaces getting zip tied, right?
Oh, okay.
So I'm wondering about zip ties here.
Oh, yeah, you put on zip ties.
You guys see that? So when they ask part B of this question, which is, does E satisfy the curl test? I'm wondering, is it smooth? Yep. Is the curl of E 0? Yep. What's the last thing?
This is the zip tie test. I guess?
Yeah, is there a zip tie, right? Can any zip tie that I put in the domain be contracted?
Yes.
Where does my domain have problem?
Zero at the point at the origin.
Yeah, only at the origin, right? So, I like that zip tie analogy. That's good. Check. Zip ties. Then what?
Well, since all that's the case,
then it's the gradient of something.
Gradient field.
Do I know what the gradient, I know what it's the gradient of?
Wave function.
No. Do I know it's the gradient of something?
Yes.
Yes.
Do you want to figure it out?
No.
Definitely.
Could you?
Yes.
Probably.
Maybe.
You might be able to.
We did number 18.
You guys cool with this?
Yeah.
Oh, is this number 18?
No, well, we did number
No.
Yeah, 18, that's it.
Number 18 is fine.
Oh,
no.
no. Cool. So, yes, we could find of what?
Gradient.
We could find a
Oh, the
scalar function for which this thing is the gradient.
Okay.
You guys all see that?